Okay. Hello, folks. Welcome to my talk. I'm gonna go ahead and share the screen. I don't think I'm gonna slideshow just because. Okay, so this is a sort of advanced version of some of my previous talks on HonestML. If you're interested in some more basic stuff with that, you can head over here, and then actually one of my previous data science connect talks is right here, and that's more introductory. But this is going to be sort of advanced. I'm going to assume that you know what a statistical model is. We're going to review it slightly. So let me go through the agenda. I'm going to assume you know what a statistical model is. Hopefully, for folks that are already aware, this review will still provide some interesting insights or interpretations for how to think about statistical models. Then I'm going to introduce the HonestML framework. Then I'm going to define and go into the guts of what a neural network is, how to build it from scratch, and some of the math that underpins it. This is actually going to be reversed, but whatever. And then we're going to go and look at neural networks in Tensorflow and PyTorch. Then I'm going to do a couple TensorFlow examples. I ran out of time to get the PyTorch example working, but I think it is a matter of just, some trivial bits and pieces to get PyTorch running. So I'm going to probably post the HonestML PyTorch example later today. Okay, and that'll be on GitHub here-ish. I'm going to put it in the examples, which I will reference later. Okay. So let's talk about what a model is. I'm going to just read the slide and then we'll go. All right, so a statistical model describes a multivariate relationship. We can think of any statistical model as the association between our dependent variable and our independent variable. So another way to think about a dependent variable is it's the thing of interest or study. So like, I don't know, if we're interested in the rate of cancer, then there's a bunch of independent variables like your age, your gender, your sex, or sorry, that's the same thing. Your height, your weight, your ethnicity, income, how much sunlight exposure you get, diet, all these things sort of like, coalesce into like how likely a population is to have cancer or whatever. And then you can take the actual number of cancer cases or the probability that you will have cancer at a given time, and then you can regress this against those variables. And so that's your dependent and independent variables respectively, right? So that's like an example with data. Anyway, so more interestingly, we can think of, well, okay, fine. So that's like what everyone cares about, the use case most of the time. But if we now go into like, all right, what the heck is a model? What is it really telling you, right? That's sort of the deeper bits and pieces. So at a high level, it's just modeling. A model is just like telling you how a bunch of stuff is related to one thing or how a bunch of stuff is related to a bunch of other stuff. That's the idea. But statistically, right, like you can sort of see that there's this line here. And this line is what gives us that relationship. So in general, models don't need to be linear, they can be nonlinear, you can have all these things. You're taking a set of data points, right? Like, so here we have, this is a car crash data set that I think comes with like scikit-learn and a bunch of other things. You can see there if you go to the source link. But yeah, you can see sort of like speeding, and then there's like, a bunch of these variables over here for the total number of crashes. And we're able to sort of get to this idealized distribution, which is this thin line around here. And then this thick line is like our guess essentially for that relationship in general. Okay. So I'm hinting at what's on the next slide. So really, a model is a description of the data. It is the same as a descriptive statistic actually. So here, I think the point becomes pretty clear when you look at it this way, but we're going to plot the mean, this red line, and then this is a normal distribution, right? And so, basically we're doing the same thing here. So this is a bunch of actual data, right? These dots are a bunch of actual data, and here's a line going through it. So I think this visual comparison makes it pretty obvious what's happening, right? So a model is really just a multivariate descriptive statistic. It is a representation of your data, and in this way, it explains the relationships between your data through this association. So I hope that's obvious. In previous talks, I go really in depth into this. So I don't want to belabor this too much. There's a lot on neural networks that I really want to talk about. But so I'm sort of being hand wavy. But I hope it's sort of obvious, and this visual picture gives you like a clear sense. Interestingly, you can kind of see that there's a normal distribution sort of like hiding here in multivariate space. In the 2D plane, and well, it's not hiding, it's pretty obvious, but and then there's like the normal distribution here. So that's the other point I was trying to drive at, is really what linear regression does, or is doing, is it's sort of saying like, okay, what if we take sort of like an average tendency in two-dimensional space, right? And we assume something normal is happening in general, in like the generalized case. Now this data is obviously not normal, right? You can see the marginal distribution. This one's like a little closer. This one looks like a skew, whatever. But like, so, in general, we assume normality for our data when we do linear regression, just as an aside. But yeah, so you can kind of see the normality of this distribution, and then the like sort of point statistic, and that's really what's happening, is there's an assumption of something idealized here for the behavior of your two-dimensional distribution, and that's sort of like being reflected over. Okay, anyway, I could nerd out about linear regression for too long, and so I'm just going to digress. Okay, cool. All right, so I want to motivate HonestML. I want to motivate the thing that's happening, what I found, why I think it's interesting, and kind of just like, I don't know, I guess shout and whine for a minute about it because it's ridiculous. But there is a solution to the problem that I found. Okay, so the problem, right? So this is really like, I honestly don't remember how or why I found this. I know I was working at this company and I was like doing some statistical things. And I think honestly, it was like, there was like a Twitter thread or something, where someone was like, what happens if you vary the random seed for, scikit-learn? So I did not like completely, I didn't come up with the problem. The problem is some Twitter thread. I think I commented on it. So like, it's documented somehow in the annals of Twitter. But I kind of was like, I got really curious and went way too deep on this. And that's why I met at the library. So all right, enough of the history. Let's go through the thing. So basically, I mean, I'm just going to read this because it's the best description. Varying the random seed in scikit-learn's train test splits, without changing any hyperparameters. You don't have to change any. For virtually every model, it causes deviance in your score. So yeah, like the question is, how can you trust the accuracy you get for any model? So like, why is this a problem? I think is probably a good place to start, because I don't think I've done a good job of explaining why this is a problem in the past. All right. And I'm going to use an example from something that happened actually last week at work, or maybe it was whatever. It's like it bleeds together a little bit. So like that last week and this week at work for me. So I'm working on this project and I implement just like a linear model, and it does great. does amazing. Everyone's really excited. Okay. Everyone's really excited. We're all really looking forward to the results, to publish the paper, whatever. And I am skeptical of the validity of the claim because I have this library. So like, all right, let me just like try the library, whatever. And we'll see what happens. So I'm going to show you the code. Well, not the code because there's proprietary data, but I'm going to show you the relevant to the general audience pieces of the code later on when we go into the TensorFlow examples. In the TensorFlow low level up API example. But anyway, so I run the TensorFlow code with HonestML, and it turns out we got a lucky train test split. And this is like terrifying to me because I don't know the statistics of how many people use like a library like mine or do confidence intervals or whatever. But I mean, because I don't think it's documented in our community, but it's certainly not high enough. And so many people are just like, oh, I'm just going to do like maybe a cross validation with 5 splits and that's enough. And in our case, it may have been, but there were enough cases where you got a good train test split that you could have believed that the model was actually good. But I think it was like 250 train test splits with the HonestML thing. Basically, and that led to a very clear, oh, if we put this into production, it will cause harm sort of level of realization, right? Like, this is clearly a false result. The problem is so many people, right? They don't do this. They just they do some naive like testing or whatever. They put their model into production, and then things fall over, and then the project fails because it's like, well, the accuracy is not as good in production. Oh no, or there's like this constant concept drift. And I think, I'm not saying this is true writ large. There are lots of situations, like for instance, recommendation engines. I think TikTok, who's been putting out a bunch of amazing papers, their privacy things are like not great, objectively not great, but like their recommendation engine and their machine learning team is stellar, like spot on, amazing. And some of the papers they've been putting out about recommendation engines and how they do the recommendation is fascinating. I highly recommend going to read it. But basically this concept drift stuff that's happening there, the way they handle it is they just have this dynamic model that's constantly training. So in a space where you have like really I don't know, promiscuous is perhaps the right word, user attention, like people are going to be really not interested in the same thing like 45 seconds later, which is a crazy amount of like turnaround in terms of concept drift. And so the model needs to be able to react to that, and update really quickly. So in that case, there's going to be a lot of this sort of like movement of your concepts. And so, in that sort of scenario, which is not uncommon in the data science realm, a lot of recommendation engine stuff is like what powers machine learning being in production and things. It's certainly not, this is like not really like the best use case, but there are so many things where the phenomenon are sort of stable and standardized. And the issue is more so that like people just don't do enough rigorous testing before they throw a model to production. And that I think causes problems. And I think that if you allow for not only hyperparameter tuning, but also like this variance of your train test split, you can see sort of like big performance gains. Now, I'm gonna make one more point, and I see the comments, and I'm gonna start looking at those. But basically, just diving really deep into this visual for a second. If you're in the academic side, like I am, your job is to write papers. Your job is to write papers and then like productionize things. And so people claim like these state-of-the-art things for a lot of these, novel architectures or whatever. They're like, oh, we beat the baseline by 0.1%. Look, state-of-the-art. Well, did you get state-of-the-art because your train test split was like, better than someone else's on some reference data set, or did you really do state-of-the-art? Now, that is not to cast aspersions or throw shade or whatever. Like, I'm sure that whatever researcher put that out there, right, their intention was to say, my idea is good and I want you to take it seriously. And usually it is. Usually the math holds up, right? Like, it's a decent idea. Community adopts or doesn't, that's their choice. But like, there's usually something there. And so my claim, though, is that chasing state-of-the-art, I think, is a silly and bad idea. It's like, I mean, we should be chasing benchmarks and realistically looking towards improvement, but we define improvement by like, did you get state-of-the-art, right? And it's like pushing the boundary, maybe like some score down a little bit should not be the defining thing as to whether or not an idea is valid. I think an idea is valid if it has merit and is clearly useful. Now, okay, I am obviously fall prey to this as well. Like, whenever I see a state-of-the-art results, I go, ooh, because shiny. But anyway, all right, I digress. So anyway, I hope that you will be skeptical, though. Just to summarize my point, I hope you will be skeptical in the future if you see a state-of-the-art results like, well, if you don't publish your random seeds and I can't fully reproduce, then maybe it's a really good idea, but maybe be a little more rigorous next time. Anyway, okay, let's look at some questions. All right, is this an overfit problem? It is not an overfit problem. Does anyone take an econometrics class anymore? I don't. Okay. So that's a fun joke, I guess. I don't know. Agreed. What business value will it provide in some sunshine? Yeah, cool. Thank you. All right, let's look at the Q&A ones. Would the random train test split leading to drastically different models be less that is larger? Oh, that's a great question. I have not run this on truly large data. Like, I guess it depends. I feel like people have asked this of me before, and I really should do experiments with this. So I think this is the breast cancer data set. Yeah, it's the breast cancer data set. And that's like, I think like 5,000 or 6,000. But the trick is, or I guess the issue is, it's expensive to run this on really large data sets, but I think I could find something bigger. I think I could find something bigger to run this against, and that would give me a pretty good sense of whether or not like this issue persists at larger sizes, at least in a way where I can prove it out to the community. I'm going to say a thing that like I'm kind of loath to say, but like, I guess, trust me, I feel yucky saying that, but whatever. So I work on a pretty large problem at work. We have like terabytes of data, and I can tell you that the train test split issue that I'm describing here gets more pronounced as your data set gets bigger, at least as far as I have found for doing regression or classification. So that is anecdotal. It is behind the garden wall of academia or Ivy Tower. I don't know, whatever. We've got all these like euphemisms. But I cannot say definitively that this is a generic thing because A, I haven't tested it, and just, B, I feel loath to say my anecdote is generalizable, but in my experience, I have found that the bigger the data set, the more pronounced this tends to be. And I'm sorry that so let me also say something else. This is very important. If your model generalizes really well, and if your accuracy is consistently good, then the train test split issue is not a big deal. And usually your variance is very, very small. So if your model really captures your phenomenon, then the variance on your like accuracy will be tiny. So there's actually a paper that I wrote with a colleague. I'm gonna attempt to look it up right now. I don't know if I'm gonna be able to. I don't remember the name. We settled on a name and I don't remember. But yeah, okay. So in this paper, we get, oh, I don't think we weren't able to publish the honest ML figures because the journal, well, anyway, we weren't able to publish the honest ML figures, but internally, I was able to show at least that on this paper that we wrote, that yeah, the train test split had a very little sensitivity to the accuracy of the models, and the accuracy was exceptionally high, like 85% precision recall, or F1 score, whatever, you know, with regularity. Anyway, okay, I digress on that point. So, you know, if your model is good, this will tend to be smaller. I think that's like a pretty good measure, right? Like you just sort of like look at your F1 score, you look at, you know, look at your precision recalls per class. My God, don't ignore that. And then, because right, your F1 score can be high, but like maybe your precision's like only so and your recall's real high, and that's like the reason why. And you know, you want to be nuanced in your analysis. But you know, if all of these things are good directionally, then you will get this nice thing. Actually, I'm going to do one more thing and then I'm going to go. I see the questions. I'm going to do one more thing really quick. I'm not going to belabor this thing in detail, but when we did I came up with this graph because of this paper, because I wasn't satisfied with what Honest ML was producing. This, I think, is the right nuanced view. And so like, I mean, the paper that we wrote, like, it was like everything was kind of up in this quadrant, which was amazing. And you know, that gave us a really nice nuanced view. So looking at precision or recall by itself isn't always the best. Anyway, okay, all right. I'm gonna go back up here for a second. We'll answer questions. Yeah, the breast cancer data set is small. I agree. Oh, okay. Oh, I guess I just have to do answer live. Okay, done. Sorry. Okay. Yeah, the breast cancer data set is definitely small. That's a fair point. But you know, the terabytes large data set, not small. Anyway. Okay, so right. So going back to this. So so all right. We've talked about the problem, the solution. So I said here embrace randomness. I feel like that's not dramatic enough, so I'm going to say embrace madness. I don't know, that's what I was thinking about. Maybe whatever. Anyway, okay. So Honest ML takes every given classifier or regressor, every given, well, I guess what I'm trying to say when I say every given classifier or regressor, what I really mean is like anything that follows the scikit-learn API, and then does the train test split. So, you know, obviously it's easy to use scikit-learn with this. I wrote it with scikit-learn in mind, but the reason why I wanted to give this talk is because I've extended it to TensorFlow and PyTorch. But yeah, anyway. Okay, so you can avoid this lucky train test split issue and thus not be overly confident in your results. And the way we do this is like, you know, it's sort of, I mean, this is not really that novel, right? I'm like kind of stealing from Bayesians, if I'm being honest, like about my honest solution. You just show the distribution, the precision, and the recall, and then like, you know, the coordinates of the precision and recall in space. And I think this is actually like really telling, right? Like you can have like really low recall and like reasonably high precision, or really low 70% or 70, whatever. But like, you know, you can see like if everything is down here, that's not as good as if everything is up here, unless, and do mind your scales, because I think it would be unnecessary to show like a bunch of blank space. So I just fit to where all the data is in this visual. I'm pretty confident in that. So just make sure you mind your scales. It's really important. But yeah, I mean, I like that, you have, and this is a Seaborn graph, that you have like this marginal distribution on the side, you recover like this extra information. And I think this gives you really what you need to be confident in your results. Like the fact that we just do like a few small cross validations and call it a day, it's not enough. It just is not enough. 200, 400 trials, I think, gives you a much better sense of confidence with respect to your data than does like, 5 random train test splits. Now, I want to say this also, cross-validation, as your data set scales, so I think this is related to the Q&A thing, or I'm trying to tie it together. Cross-validation is a more viable solution as your data set scales up, because you can do more cross-validation splits, right? You can specify like 100 or 1,000 if you have like a billion rows. You can't really do that if you only have 500 data points, but you still want to have confidence in your results. So for instance, I'm in the medical space, obviously. I mean, this is on acute kidney failure in prematurely born babies. So, there are only 200 data points ever. We're never going to get more than that. We're not going to 1 billion. We're not going to 100 million. The thing that I'm working on that has like a lot of data is an administrative problem. We're doing like health economics. That thing has like tons of data because we're looking at like hospital-wide measurements and all this other stuff. But any disease type or anything like that is always going to be small data. And so I think cross-validation doesn't serve that community of like sort of small to medium data concerns super well. But HonestML, I think, does fill that gap, because with my framework, you're just doing one train test split at a time. And so you don't run into this issue of, well, maybe there's only going to be 5 samples in my, validation set. No, it's always going to be, your third of the data or a fifth of the data, whatever you have space for. So that's why I think this solution has merit in many contexts. And it's pretty fast, and it does scale to the like billions of rows case as well. I mean, training the model slow, all that stuff, doing the predictions isn't quick, but it scales as well as anything does, unless you're using CUDA. If you use a CUDA device, oh my God, everything is just lightning. I'm just going to shameless plug for a second. If you have the option to use CUDA GPUs, NVIDIA, oh my God, do it immediately. It's amazing. Anyway, all right, let's take some more questions. Synthetic reviews will increase the number of samples. I think it really depends on the problem. Sometimes synthetic data is really useful. Sometimes you just can't do it. So like in the medical field, you can't use synthetic data for most things. Like you can't, the community won't buy it. No one will care. It's not useful. Yeah, so unfortunately for medicine, no. How is this affected by SMOTE? So Hona, maybe can you ask a slightly more nuanced question? I mean, I'm gonna comment on SMOTE in general for just a second, but HonestML is not looking at unbalanced data. So I'm not accounting for a balanced or unbalanced classifier at all. If there is unbalancedness in your data set and you want to like do a stratified sampler, I at present do not account for that. Although like doing something with balance where you under or over sample in your train test split, might be interesting for me to look at. But yeah, I don't have functionality for that right now. Like my train test splits are naive, sort of on purpose, to be honest. But I think having the ability to do some sort of stratification might be interesting to make sure you're getting like certain kinds of samples. Although, like, given how many just like of these things I'm doing, I don't know if it would really tell you anything different. Like, I'm not trying to put my thumb on the scale with this library. The goal is not to build the best possible classifier. It's to assess the correctness of the classifier that's already been built, right? So this should happen like after hyperparameter tuning as sort of like a next step. Presumably you've either rebalance the weights on your majority minority class, if you're doing like logistic regression or something, or you have I mean, yeah, so with the trick with SMODE is like you do have to do the rebalancing on the data set itself. So that's a little bit dicey. Yeah, you know what? I'm going to take that as a note. I'm going to look into it for sure, but I would love if you would give me a little more clarity on the question, so that I can think about it some more. But yeah, I think that's like fair. I should add that as a feature, as some sort of like rebalancing thing, just to see if a SMOTE does make a difference. So I'll probably do that next week. But yeah, okay, let's check over here. Embrace the madness. Thank you. Do you recommend getting this distribution after you've already completed final? Yes, I do. I do recommend that strongly. Thank you, Evan. I'm glad I answered your question without meaning to. All right. So anyway, all right. So now that I've kind of like walked through some stuff, I guess I'm just going to say like the definition out loud. So HonestML is a framework to do more honest model development by testing a vast number of train test splits to ensure your model's accuracy isn't due to a lucky train test splits. And then, so for me, this method is the next step after you get a good enough model using cross-validation and you've done all your hyperparameter tuning and all of that. Yeah, okay. Are there more Q&A things? I'm just gonna, oh, no, wait, oh, I have to click done? Wow, that's weird. All right, anyway, whatever. And then I've got docs up and I've got the source code here. So source code and then the docs right there. You're interested. Yay. Okay. Anyway. Okay. So we've got a little less than half the time remaining, so we can do neural networks. Hooray. I want to like really explain what a neural network is. That's really important to me. All right, I'm going to check the chat before I dive in because I'm going to talk for a while. Just a while when as I start doing that. Yeah, I would say that that's fair. I mean, I don't know if it's ideal for categorical variables, pure oversampling. Yeah, I'm actually not 100% sure. I don't think I've done any experiments with this. This is an interesting point, though. Thank you for sharing that. But yeah, okay. All right, I'm gonna talk for a while, and I'm not gonna check the chat for a little bit. So, neural networks. Yeah, the spicy magic. Okay, so obviously everyone cares about neural networks. They are super neat, fantastical, amazing, right? We can chat GPT or style transfer or generate images. Or I don't know, do like a bunch of magical, crazy stuff, search the internet, just kind of whatever you want. It's amazing. Segment anything. That model looks so cool. Like, good job, FAIR team. I think, yeah, it's definitely Facebook's AI team, research AI team that did it. That thing looks so cool. I can't wait to play with it. There's like so many fun things. Anyway, so neural networks are neat. Everyone agrees. So let's go learn how to build them. It'll be fun. Okay, so there are two really big components to neural networks. The first one is stochastic gradient descent. The second one is like the dot product from linear algebra. So the fundamental idea behind stochastic gradient descent is really simple, and you can see it being played out right here. You basically start with some point, you take a guess, you try to find your second point, you take another guess, and so on and so forth. And you're really trying to get to this point here. This point here is your solution. The solution to the question, how do I optimize my function? How do I get the zero for my function? And you can use, as you can see, these lines, right, to get closer and closer and closer to your zero. Now, obviously in linear space, any 5-year-old can sort of see, oh, look, this line, this function line, just kind of comes in right here, right? So this linear, this two-dimensional space example is like fairly obvious. But what happens when you can't visualize your plane? What happens when you have to do this in 15,000 dimensions or 20 million or whatever? Or I forget how many parameters ChatGPT has. It's in the trillions though, right? So, I can't find this line. I can't find this point. I don't know where the zero is. And that's why the gradient of a function is so powerful, because it gives you a sort of way of guiding yourself towards a solution. So we don't have functions in the machine learning space because we're trying to realize them. But we do have examples, and we can take gradients of loss functions. So I sort of lied. We do have functions, we just don't have the function of interest. But it turns out that this problem of finding the zeros is related to this problem of finding an optimal function. We can find an optimal, if we think of a zero as a subspace in two-dimensional space being projected down to one-dimensional space, we can think of a sort of zero, an optimization, an optimal function representation as sort of like the zero in or the subspace of interest. So subspaces is like a term from linear algebra. Basically what you do is, like, let's say you're in R3 and you want a subspace in R2, right? So you're looking for a two-dimensional matrix and a three-dimensional, well, okay, sorry, no. You have a 3x3 matrix and you're looking for the 2x2 submatrix. That's what I really am trying to say. So the 2x2 matrix would be R2 and the 3x3 is R3. So that's like the nice thing about linear algebra, is that these matrix representations are what get you to your subspaces. And so we can always think in 2 dimensions, even though as our matrices grow, really we're dealing with tens or millions of dimensions. And so it's like a really nice representational view. And there is this geometric interpretation as well, which allows us to do like optimization and then visualization, at least sort of naively. Okay, anyway, so we're going to review we're going to motivate some linear algebra, and then we're going to review it a little more. But yeah, so this curve finding thing, right? Or sorry, the zero finding thing. We can do this with Python, right? Pretty obviously. So here we want to find the zero for equation 1. And we can do that with just guess and check. It's so dumb, but it works. You can brute force it. You can just go through, assuming that your equation is really stupid. This gets harder, as things, but yeah, anyway, so you can find for really simple equations, you can also find exact examples. This gets more sophisticated as you move into more sophisticated equations. I used a generator. Ooh, magic. And so like we get more nuanced and more sophisticated, and this keeps sort of happening as our equations get more complex to find the zeros. And like I couldn't even do these. So this one I have 4 parameters. This is 1 parameter, 2 parameters, 3 parameters, 4 parameters, and here I'm passing in. This is like the constants. And it's coefficient variable, and then we're summing. So like, you know, it gets expensive. It gets very expensive. But yeah, okay. So like, this is the point I'm trying to make, is that like, and this is like, you know, sort of nerdy Python optimized, but brute force only gets you so far. If we want to sort of guess and check intelligently, then we ought to use linear algebra, because linear algebra is awesome and allows us to optimize a system of equations, you know, like pretty much simultaneously. It uses, like, in a sense, more math than this, but in another sense it doesn't. And actually we get dynamic programming for free using fast Fourier transforms, because we're able to look at repeated calculations within the linear algebra that's happening and sort of say, oh, I've done this already. Let me just like do a lookup. So the fast Fourier transform allows us to do linear algebra like blazingly fast. If you aren't aware of what I'm talking about, because I'm not going to go through that in here, you know, you should absolutely check out Veritasium, and what is it? It's three blue, 1 brown. I can never remember whether it's 3 brown, 1 blue. I think it's 3 blue, 1 brown. Those 2 channels on YouTube, they do a fantastic job explaining fast Fourier transforms. I would recommend both. They're complementary. They don't cover the exact same material, but yeah, and it explains how the dynamic programming works, and why fast Fourier transforms are like literal magic. Well, they're literal computer science concepts, but they appear to be magical. Anyway, all right, anyway. We're gonna skip over the supply and demand example. I mean, this is how you do row reduction, which is like a way of taking any matrix and then getting it down to an optimal solution. So basically what you do is you start with some matrix, you get it to the identity matrix, and then you have some associated vector that comes along, and you apply the same linear transforms to that thing, and then you get a solution. So this is the idea behind optimization within linear algebra. And so it turns out that invertibility is really like the key idea for how you do optimization within linear algebra. Everyone asked the question, is the matrix invertible? Because really what we're asking, is the series of equations solvable? Can I come up with an optimal solution? Are there zeros? Is there a subspace that is optimal that I can write down a function for? Ooh, interesting. This sounds like neural networks almost. Okay. So I wrote down a little solver for linear algebra. I'm not going to take you through all this code. It's way too much. But basically, we start with this matrix like we did above. And look, lo and behold, we end up with the solution. Hooray! I don't remember what these prints are, the 1001 thing, but don't worry about that. And I'm just going to verify, you know, this is the same. So 1 negative, okay. 1, 2, is this, maybe I did a different one. I think I did a different matrix. Yeah, I did a different matrix. Doesn't matter. Whatever. It's interesting it came out with the same values. That's weird. But okay, so we're just going to go through matrix operations for like a second, just you can see what's available to you, and like they're really simple. So this is addition. You go like, okay, so 1 here, 1 here, right? So it's row and column. That's how you decide. So like the 1 and the 1 get added, and that's a 2. The -1, sorry, the -2 and the 1 get added, and that's a -1. The 1 and the 1 here get added, that's a 2, and the 2 and the 1 get added, that's a 3. So like matrix addition and subtraction are really easy. You just are like, okay, here is the ijth, I as in you know, row index, and then j as in column index. So the ijth entry, in this case 0, 0 or 1, 1, whatever notation you prefer. I guess computer scientists would say 0, 0, algebraists would say 1, 1. because they count starting at 1. This actually was a very big row for me in graduate school. I got 1 point off one of my homeworks because I was trained under algebraists until I trained with a number of theorists who really likes computers, and there was some infighting, but it all turned out fine. Anyway, whatever, I digress. But like, no one can agree where to start the natural numbers. It's really interesting. So, addition and subtraction is really simple. The formula is trivial. Multiplication is a little tougher. It's a little tougher. So if you want this entry, you have to go across this entire row and then down this entire column. And I'm only going to do the one because it's ridiculous to do all of them. You can, as an exercise, do the rest, but it's the same thing. So if I was on a piece of paper, I would just draw a line through this, and then I would draw a line through that, and then it would collect the terms. So 1, 2, right? 1 times 2. So you do the multiplication based on that position relatively. Like, think of this as like a list, and this is like another list, and then you go across the indices. So the values in the first position of the matrix, end up here, and then the values in this, of the list, and the second position end up there. So then you get the 2 and the 4 this way. Okay, and then you add these up after you multiply, and that's how you get the 10. And you can do the rest for all these, and you'll check that these numbers are the same. So this is really important, actually. The last thing I want to talk about in multiplication land. This is not true. This hurts a lot. This hits a lot of programmers pretty hard. I don't know why the idea that matrices are not commutative. If they were commutative, then A times B would equal to B times A. But this idea is really, really hard for a lot of computer scientists. I see a lot of junior engineers making this mistake when they want to get into machine learning. So I'm going to hit you over the head with it a little hard, in case anyone wants to watch the recording. And this is like a thing that they've been stumbling over. But this is, I think, what makes machine learning programming hard for a lot of people. And it's not something that happens actually even just to junior people. I've run into this problem. Like, it's so easy to forget about commutativity. Because it's just variables, right? Like, looking down here, this is like the Python equivalent to the dot product. If you just switch this A and B, you would think, oh, why is this coming out different? And then you have to remember, oh yeah, commutativity. But really the reason why, and this is why I think, maybe having some representation of our matrices and just printing things as you go is really important, or thinking about these things. This is not the same as this, right? These are two different spaces. If you want to think about it that way, like this is, R3 and this is R2. And the fact that they work is sort of like a fluke, because we're taking 3 components of R2 and 2 components of R3. So like, these are different spaces. If those numbers don't line up, then there's no reason that should work, right? You shouldn't be able to take arbitrary spaces and mash them together. And so that's why you lose this commutativity. And so I think that's fine. This happens to work out in this case, but it's not always such. And so when you're implementing specifically a neural network from scratch, a lot of this stuff can be bad. All right. I'm kind of running out of time, so I'm going to skip over some stuff. Whatever. This is how you do a dot product. And then, yeah, invertibility, amazing. Okay, so I'm going to show you sort of like why we care about linear algebra, and then I'm going to go through the TensorFlow examples, and I'm going to show you the neural network from scratch implementation. So generate some random data, and then we're going to take the transpose of the dot for this thing. And then this is the optimization step, this inversion here. This is really important. This is what's doing linear regression. I said, I promise, like linear algebra for neural networks. Why am I showing you linear regression? Just because it's a simple model. And we don't have to do stochastic gradient descent using this. Now, why do we prefer this over stochastic gradient descent typically when we're actually programming these things? It's because we've learned how to make linear algebra really fast, thanks to fast Fourier transforms and other optimizations for linear algebra. We can make additions and multiplications quick. Due to TensorFlow and PyTorch and all these other neural network frameworks, we've gotten much better at implementing, the gradient stuff, but historically linear algebra was much faster than gradients or calculus, and so this is like the preferred method. Plus the code's just like really clean and short. Anyway, so we do this. This is the optimization step, and then we just basically combine things back. So this is like setup. This is setup. This is some crazy magic. So yeah, doing linear regression in one line is pretty freaking awesome. Okay, so let's do a neural network. We're gonna just go into the implementation. So this is a generic dense. I'm doing it for 10H sigmoids. You know, I could do a linear one as well. That would just be linear regression. So this is actually hiding a linear dense layer as well. Like this is a linear dense. This is what you would do. And I'll sort of show that when I go to the TensorFlow example. But yeah, so here you can see that we are picking on our activation. And this is sort of like the way that I'm doing the calculus is I just literally hand code the derivatives. That anything with a D on the activation is just the derivative of the function. And this sort of like cheat works for really simple things where you can write down a derivative. But like, you know, not all of your activations are going to be so simple, and it's like nice to have a framework. So like, you know, we have these automatic differentiation frameworks, which are freaking awesome. Okay, so in general, if you want a neural network, you're going to have a forward pass. This is just doing the dot product that we've already talked about. And then matrix multiplication is just literally how you chain things together. It's how you chain your data together and pass it through your layers. So, you know, you can kind of see that's really what's happening. You're taking your previous layer, you're dotting it with your current layer, and then you get some outputs. So, you know, you computing your gradient, also just using more linear algebra. It's just, you know, linear algebra is the glue of neural networks, which is why I belabored the points so hard. But then if you want to update your weights, it's pretty simple. You, you know, get ready for your multiplication, you do your dot product, you update, and so on and so forth. Okay, so that's like a dense, which is really where most of the magic happens. You push the work off to here. And then my network is pretty clean. So this is my implementation, obviously, that wasn't clear. Basically, you do your forward pass, right? You update your layers and so on and so forth. And then the back propagation is a little trickier because you have to flip. You compute your gradient, you kind of go, you're going backwards through your layers, and then you update your weights. But yeah, you can kind of see that here. It's just all linear algebra hidden underneath and doing dot products. You're not doing the inversion. You're using the stochastic components here, right? This computing the gradients and then the error updates in order to actually get you know, your errors to propagate and to optimize. Okay, anyway, so you can see the full thing being run out here, and this is, you know, all up on the internet, but you can see, oh look, it works. Hooray. Okay, so that's what I wanted to go through for explaining neural networks. Let's go through some TensorFlow examples, some PyTorch examples with honest ML. I'm just going to make sure that I'm not missing anything. Yeah, okay, great. So we're going to do a really simple example with the Keras API first, and then we're going to go through the low-level TensorFlow API just to get a little palate cleanser. I've got 5 minutes left. We're not going to get to PyTorch. I'm sorry. That is my fault. I plan too much. I always do. It's just the nature of life. But yeah, okay. So, and then I'm going to try to take the question that has been lingering, and I apologize for that. All right, so let's just go through. This will be pretty straightforward. This is a standard, really simple neural net. It's using a ReLU, and then a sigmoid. So this is just doing classification. And so happily, Keras does work out of the box with my framework. Hooray! It handles pandas data frames intelligently. You know, it's sort of like obvious what's happening. And then, yeah, we can just pass things through. and do our visualization. So this is where HonestML, shines. You get to see the precision and recall for all your classes. And then, yeah, that's kind of that. Then here's a regression example, really not any different. You can see your MSEs. And so like, depending on your problem, I'm actually just going to belabor this for a second. There's a really pretty stark difference between this number and this number. And depending on your train test split, some percentage of the time you're going to get this. Maybe that's not okay. Maybe a model can't ever perform like that for some new swath of data, and that would be really, really bad. But maybe, if you're in a certain business use case, getting around like 40,000 error might be okay. Like it really depends on the scale of these things, right? It always matters. Scale always matters. People don't think about this enough. Like I think everyone's like, oh, my MSE is less than 1. I did great. Well, compared to what, right? Like these error measures are kind of unitless. So you have to think about the units on your actual data and then tie it back to your use case. So for instance, one of the things that we do at work is we're really interested in the number of records that we're getting from the database over time. And we're generating billions of rows a day. So if we're off by 40,000 from what we expect, that's a good day. We did great. I'm not going to explain any of the context behind that for many reasons, but like, that's a great day for us. So like, it does depend. Like if you're off by 40,000 in a billion, like you did amazing. Like your regressor is spot on. Like that is accurate. But, if you're off by a trillion and you only got a billion records, that's not great. All right. So let's go through the TensorFlow low-level API. This is up on GitHub, by the way, so you can see this as well. But I did want to take you through it because implementing a neural network from scratch, I think, is super important. So the denses I'm just going to use. So this is the problem I was working on at work. The denses I'm going to use from Keras because they're faster than the ones you would implement yourself. I'm using a custom loss function here, which I think is really interesting. It's custom in a sense, like it's coming from TensorFlow. You can write your own custom, loss functions as well. I do have an example of that I want to put up, but I didn't have time to get to it. Anyway, so you provide your call, which sets up the order in which you want to do your layers. And I think using the low-level API is really nice because you can specify a lot of control here. Like right now, what I'm doing is sort of this linear sequential thing, but there's nothing saying that I'm just going to, you couldn't do like self dot. I'm going to pretend I have like a different value there, and I could do it on X and then do like a res2, right? And then maybe I do like, I'm not gonna look up the syntax live, so maybe there's like some res plus res2. I'm not claiming this is correct. And then we like apply like a self.final layer to this thing and then return that instead, right? Like we just have so much flexibility to just sort of do this sort of a thing in a really like obvious way. And this would probably be like a TF concat or something. I don't know, whatever, but you get the idea here. I'm just trying to draw your attention to the fact that you have flexibility in how your layers are sort of manipulated in this like really procedural way, which is nice. Anyway, so I really like the low-level API. This is actually what I use at work 100% of the time. I do not use Keras. I do not use PyTorch because I don't think their low-level API is good enough, to be honest. But yeah, I think TensorFlow has the best low-level API available today. At some point, JAX is going to overtake it, and that's going to be a great day because JAX is magic. But like for right now, TensorFlow is king, I think, when it comes to the local API. Anyway, so you know, you need to provide a fit method. This is just for HonestML. You need to find provide a predict method. The fit method is going to be trivial. It's just literally calling step, as you can see, and you don't need to return anything or whatever because fit doesn't return anything. And then predict is just using this call function. Now you can either do dunder call or call, doesn't really matter. They both work. You do need a get coefs and a get params. This is like a nice little thing. It works because these are linear layers, so you can take a set of linear transforms and always combine them. But like if you're using nonlinear layers, this will not work to get the coefs out. I would just set the coefs as none. Like just like in the initialization, just set the coefs as none. I also don't set any hyperparameters. This obviously you can choose to do, which can be useful. So in my thing, I allow you to write out your hyperparameters to a file using this experiment thing, which is really fun. All right, I'm gonna look at that for like a sec. You know what? No, this is my work computer. We're not gonna do that. I want to show that whatever. There's documentation on the experiment API. Please go check it out. All right, and then we have the visualizer as the standard, and we can write stuff out, which is cool. So you can see the MSE and everything else. All right, so I am gonna stop sharing and answer questions for like a second. I know we're 2 minutes over, but yeah. Where's the chat? Oh, I thought there was a question in the chat. Okay, yeah. Oh, thanks. All right, they just literally said 3 blue, 1 brown is great for the Fourier transform. All right. Well, I guess that's it then for my talk. Thanks so much for coming. I really appreciate it. And yeah, I hope you all learned something and had fun. All right. I don't know. Do I just stop the recording or do I just end the meeting? What do I do now? Oh, actually, you know what? I'm going to take a couple minutes for questions. If there are any questions from folks, please feel free to ask. I'll stick around for like 5-10 more minutes if people have questions. I'm sorry we didn't get to PyTorch. Truthfully, I do have a bias. I like TensorFlow more, but like, you know, it's still a good framework. And I am going to put up like the code to explain the PyTorch examples pretty soon. It's just a little bit, the low level API is not as good. I mean, PyTorch code is beautiful and elegant, and there's so many things I like about it more than TensorFlow, to be honest, but they just, they don't make it as easy to do low level things, and it's just annoying. I mean, their design choices, the frameworks are very, very close, but there's just that little bit about TensorFlow that I like a little more. But anyway, whatever. Yeah, if there are any questions, oh, thanks. If there are any questions, I'm here. So I'll stick around until 11:15 a.m. I'm in Eastern Standard Time. So I don't know, the next 6 minutes. But yeah, if anyone has anything, feel free to ask in the chat or raise your hand or whatever. But yeah, that's it. I'm just gonna hang out. If no one has any questions, I don't know, I could juggle. Which is like my way of killing time when I'm just on a Zoom call and no one's talking. Yeah, I've got juggling clubs, so I can do that. Where do we access the code? Okay, that's a great question. So let me give you that. All right, so the code is at HonestML. Actually, let me share my screen so I can not just put it in the chat. So this is where you can get the code. And then if you want the examples, it's all right here, and you can see the TensorFlow stuff. Like I said, the PyTorch stuff isn't up yet because it's not finished. Almost done, so close. If you're interested in going over the TensorFlow or the neural network stuff in detail, that's over here. But that'll be in the slides too, which should be up at some point. I don't know. I think we're going to share the slides. But yeah, boop, and then that's that. All right. No. Other questions? You're welcome. 4 more minutes. How's everyone's week going? All right, I'm gonna juggle if there's nothing else. No, I don't know. It's weird. Should I? Okay. Does anyone actually want to see me be a clown? I guess it's a better question. I never ask. You know what? I'm just gonna do it. And if more questions come in the next 4 minutes, then they come. If they don't, they don't, you know, like whatever. I'm just gonna have some fun with it. It's never that entertaining for very long, but it's always entertaining for like 10 seconds. So that's why I do it. Okay. All right. Oh. I'm going to be using my light clubs today because the heavy ones hurt. Oh, I was not ready for that. I am not awake. Okay, there we go. So weird when you transition between skills. All right, we got 3 minutes left. There are no questions. I can also answer questions while I'm doing this. Super fun. All right. You got to see my random skill. Ray. Oh, 3 more minutes. Well, I killed 10 seconds worth of time. Like I said, it's fun for 10 seconds, and then it's just like a little weird. Because then you're just like throwing clubs. People are not doing anything. It's very strange. All right. I'm going to end a minute early if no one else says anything. So at 11:14, I'll get out of here. If no one has any other questions. All right. I'm going to guess that's no more questions. Yeah. Okay. I'm just going to end then. Well, thanks everyone for coming to my talk. I hope you had all the fun in the world. I enjoyed it. It was good times. All right. Bye. And webinar 4.